Hi, it's Miss Murphy. So today we're going to look at an intro to gas laws. We'll start with kinetic molecular theory and look at how these different variables, let's get started. So when you think about gases, right, picture a gas in your head. Let's see, let's draw a little demo here. Let me share my screen. Coming, 1 second. Come on. Okay, so right, what we have here is our kinetic molecular theory. All right, it's commonly referred to as KMT, stands for kinetic molecular theory. The kinetic molecular theory is based on experimental observations about the behavior of gases. So recall, when you think about a gas, right, these particles are spread as far apart as possible. Let me move that. There you go. So let's look at some of these postulates. Postulate 1, large number of particles in gases that behave like hard spherical objects in a state of constant random motion. So that tells us that our little gas particles over here are constantly moving in random motions. All right, they move in straight lines until they collide with another particle or the walls. Okay, the particles are much smaller than the distance between them. So we assume that the particles themselves take up no space, right? That is an assumption that we'll later find is true for ideal situations only. There is no force of attraction between the gas particles or between the particles and the walls. So what that means is there are no IMFs present, right? No intermolecular forces. That also is an assumption that is only true under certain ideal conditions. The next postulate is collisions between gas particles with themselves or collisions with gas particles and the walls of the container are perfectly elastic. What does that mean? It means when they collide, they bounce right off of each other. They leave with as much energy as they came with. Unlike when you drop a rubber ball and it bounces and the balls steadily have a smaller bounce, that is an inelastic. That is where you see the energy is lost with each bounce, or each collision. But here, when gas particles collide, no energy is lost. And then the last postulate states that the average kinetic energy of the gas particle is dependent upon the temperature and nothing else. All right. So let's now take that and look at some of our gas laws. When you talk about gas laws, it's just a series of equations that relates the different variables that affect gases to each other. So when you think about a gas, right? Once again, here's our container. Here are our gas particles. They are moving in random motion, all right? Colliding with each other and with the walls of their container. What variables, factors, affect the behavior of these gas particles? Well, as some of them are brought up here, temperatures, right? We know that at higher temperatures, the particles have more kinetic energy, so they're colliding with the walls of the container with a greater force. Thus, we create a pressure. So pressures and gases go together. And it's also true that a gas will expand to fit the volume of its container. So the volume here is always a factor when we're discussing gases. The other variable in terms of gases is the number of particles of gas, right? And recall that we don't count particles because they're too small. So we will group them into moles. So we will not count the particles, we'll count the moles of the gas, all right? So you'll see that throughout this entire unit, we will be discussing temperature, pressure, volume, and moles of gas, all right? All about gases, no intermolecular forces. That's solids and liquids. Temperature will be measured in kelvins, all right? And recall that a Kelvin is equal to a degree Celsius plus a 273. Some people say 273.15, particularly Brain Genie, all right? I often just do 273. Pressure is measured in many different units. We can see atmospheres, millimeters mercury. Literally, they measure the millimeter, the height of the mercury to determine it. We'll look at diagrams of that. There's something called torr, and we'll also become introduced to kilopascals. Let's talk about these pressures a little bit more because we need to be able to convert between one pressure unit and another. So standard pressure is equal to 1.00 atmospheres. What does that mean? That means that when you walk outside, the typical pressure of the atmospheric gases pushing down on you is equivalent to 1 atmosphere. It is also equivalent to 760 millimeters mercury, which is equivalent to 760 torr. What that means is millimeters mercury and torr are identical units with different names. Torr is the name of the scientist who came up with the millimeters mercury concept. So they are identical. And then we've got the 101.35 kilopascals, all right? All of these are standard pressures. They are all equivalent to each other. 1 atmosphere is equal to 760 millimeters mercury, is equal to 760 torr, is equal to 101.35 kilopascals. So those are my conversion factors. I can convert between any of these units, right? For example, if I have a pressure of 775 millimeters mercury, I can say that every 760 millimeters mercury is equal to 1.00 atmosphere. And I would easily have my pressure, not in millimeters mercury, in atmosphere. Notice this should be greater than 1, right? So greater than standard pressure. And this would be 1.02. Okay, so you need to be able to convert amongst your units. Okay. And then a volume, right? The amount of space that the gas particles have to take up, to roam around in, and we assume that the gas particles themselves do not take up any space, so that the size of the container is available, the entire size of the container is available. Volume is typically measured in liters. Yeah, we'll leave it at that. All right, liters, and then I'll go L. All right, so now let's look at the gas laws. Once again, what these gas laws will do is they will relate temperatures, pressures, volumes, and moles, okay? Let's make this smaller so that I have a little bit extra space. You may want to pull out a separate sheet of paper to attach because you can't do this. Oh man, let me do this one more time, okay? Let's undo that. Okay, so the first law, you can go ahead and write it down, is going to be called Boyle's law, as in B-O-Y-L-E'(S). okay? Boyle's law is going to relate pressure and volume. And we are assumed here to have a constant temp and number of moles of gas. Because if they were changing, we would need to account for that, but they're not changing. Pressure and volume. Pressure is caused by gas particles pounding against the walls of the container. As the volume goes down, the gas particles are going to have less space to roam. They're going to collide with the walls of the container more often. There's going to be a greater pressure. So we have an indirect relationship. What that means is one variable increases, the other variable decreases. Pressure goes up, volume goes down, volume goes up, pressure goes down. Typically, it's the volume that's causing this change, right? We change the volume and then the pressure is affected typically, all right? The mathematical formula simply says P1V1 equals P2V2. So these would be my initial conditions. And these would be my final conditions, okay? And we'll do a couple practice problems when we're done looking at the gas laws. So you just plug them in and you just do the algebra. It's very, very simple. Pressure goes up, volume goes down, and vice versa. We've also got, next, let's do Charles's law. Okay, Charles is going to relate volume and temperature. So here we'll have, Charles's law. Okay, and this will relate volume and temp. Since we do not see pressure and moles here, they must be held constant, okay? Pressure and number of moles not changing. Okay, they are held constant, therefore they are not in the equation. If the temperature goes up and the pressure doesn't change, because if the temperature goes up, we move more quickly. We collide with a greater force against the walls of the container. Well, but we see that our pressure is constant. The only way to do that is to simultaneously expand. So we will see a direct relationship here, right? Where if the temperature goes up and the pressure must remain constant, then the volume itself must also go up, right? So we've got a V1 over T1 equals V2 over T2. Your temperature here, guys, and so many of you are going to make mistakes, your temperature must be in kelvins. You cannot plug a Celsius temperature into this equation. Celsius temperatures go into the negatives. Kelvins do not. If you have a negative temperature, you're going to solve for a negative volume. It doesn't make sense. You have to use kelvins always. Always make sure your temperature is in kelvins. The only time your temperature does not have to be in kelvins is if it is a change in temperature. All right, let's look at another law. It's going to be the Gay-Lussac's law. Okay? He's going to relate pressure and temperature. And so if we're relating pressure and temp, the volume and moles must be held constant. Okay? Now, if the volume is constant, but the pressure goes up, what's going to make the pressure go up? The temperature going up. So if the temp goes up and there's no extra room and we're moving more quickly, then we're going to be colliding with the walls of the container more often, and we're going to see that pressure increase because the volume is not giving here. So once again, we will have P1 over T1 equals P2 over T2. Make sure that your temperature is in kelvins, all right? It must be in kelvins. And then we can almost finish this up by doing Avogadro's law. And he states he's going to deal with pressure and moles such that temperature and volume are constant, okay? And there's a direct relationship between the number of particles in the container and the number of collisions with the walls of the container. So as the number of particles go up, the number of moles or the pressure will definitely go up. So as the number of moles that's going to be in, actually it's going to be a small n, and I should write that up there, increase, then we'll definitely see an increase in the pressure. So we've got P1 over N1 equals P2 over N2, okay? Now we've got one more equation at our fingertips, and that equation is going to combine all four variables. You see why these are called the gas laws. It's just equation after equation after equation. If I take the combined gas law, which is, let me just write it, it will account for all variables where nothing is held constant, all right? So notice that in every gas law, let's start at the beginning, we've got P and V on top, and then in the next gas law, V is on top and T is on bottom. And then in the next gas law, P is on top and T is still on bottom. And in the next gas law, P is on top and N is on bottom. So what that tells me is that P and V are always on top, all right? And the temperature and the number of moles of gas will always be on bottom. That's because of how they're related directly versus indirectly. Anything that is next to each other, well, I don't want to say all that. Okay? Now, temperature must be in kelvins. This equation right here relates everything. If you can remember this equation, then if volumes are held constant, then you can literally remove the volume from the equation and plug everything else in. If the volume and the number of moles of gas are held constant, then you can just omit both of them and you've got P over T equals P over T, right? Go backwards. If I was dealing with pressures, volumes, and moles, and the gas and the temperature was constant, I would just remove temperature from the equation. All right, let's finish this up because this is taking too long. Here's a couple practice problems. 6.0 liters of a gas. Well, liters is a volume, so let's call that volume 1. Is at a pressure of 1.0 atmospheres. So this volume has a pressure that is 1.0 atm. It is compressed until the new volume is 3.5. That's a new volume. We'll make it 2. And it is still in liters. That's good. The question is, what is the new pressure? So we need the pressure at our new temperature, our new volume. So look at your variables here, right? We've got P's and V's and P's and V's. We're left to assume that the temperatures and the moles are not changing. The gas law that relates pressure and volume is Boyle's law. P1, V1 equals P2 times V2. Plug and chug, guys. 1.0 atm times 6.0 liters equals P2 times 3.5 liters. A little bit of algebra. Divide both sides by 3.5 liters. And the pressure, right, this cancels. The pressure is equal to 6 divided by 3.5. 1 times 6 divided by 3.5. It's a little bit less than 2. And what we've got is 1.7 atm. Super simple. A lot easier than stoichiometry and all that stuff. All right, let's go look at another example. A balloon, 35 liters of helium. So we'll give that a volume of 35.0 liters. The temp is 20 degrees Celsius. So we've got this volume at temp. As soon as I see a degree Celsius, I tell myself, no, I need kelvins. Go ahead and add 273, and we've got 293 kelvins. By noon, we have a new temperature, so that's T2 equals 45. Once again, as soon as you see Celsius, go ahead and add 273 and get 318 kelvins. What is the new volume? So V2 equals question mark. Okay, so I look and I see I'm dealing with volumes and temperatures, therefore pressure and amount of gas particles stays the same. I know that V1 over T1 equals V2 over T2. That is what Charles's law. So let's just plug those guys in, right? Let's get a green here. 35.0 liters is at a temperature of 293 kelvins. And our new volume is at a temperature of 318 kelvins. So if you're looking at how to solve this, we will cross multiply, right? In this situation, you will always just cross multiply to set up your algebra. And we have 35.0 liters times 318 kelvins equals V2 times 293 kelvins. Go ahead and divide both sides by 293 kelvins and see that your kelvins cancel. You're left with liters, that is a volume. The answer is 35 times 318 equals, divided by 293 equals. And that's going to be what? It's a perfect 38.0 liters equals V2. All right, one more. Okay, we've got a helium balloon at a pressure of 1 atmosphere. P1 equals 1.00 atmospheres. A volume of 4.0 liters, temperature of 20. So V1 equals 4.50 liters. T1 equals 20 degrees Celsius. Add 273, right? Just go ahead and get your kelvins so you don't forget. All right, it's released. What volume? So we're going to look for our new volume. When we have a new pressure, we get up higher where the pressure is lower. So our new pressure is 0.600. So that low pressure would make our volume go up. And the temperature went down, which would technically make our volume go down. So let's see what actually happens. Notice we've got negative 20 degrees Celsius, add 273. That's going to give us 253 kelvins. Now let's look at our variables to see which gas law we should use. And I see pressures, volumes, and temperatures. So it looks like I could use my combined gas law if I just took the moles out of there, right? So let's go down here and let's say that for this problem, we will use P1 V1 over T1 equals P2 V2 over T2. All right, start plugging and chugging. 1.00 ATM. Keep your units. It makes for good work and allows you to check yourself. If you don't end up with the unit that you need, you've done the wrong steps. And let's see, we do have initial pressure. We do not have an final volume. That's what we need, but we do have a final temperature at 253 kelvins. Once again, we're going to cross multiply. So it's going to be this times this is equal to this times this. So 1.00 atmospheres times 4.50 liters times 253 kelvins is equal to 0.600 atmospheres your new volume, and your old temp, right? So I'm going to divide both sides by 0.600 atmospheres and 293 kelvins. All right, so what you see is that my volume is equal to this times this divided by this. And look at your units, atmospheres, atmospheres, kelvins, kelvins. You're left with liters. You're solving for a volume, appropriate unit. Good. Okay, I've had times as you progress and things get harder where literally the units tell me how to answer the question. So don't take your units for granted, okay? Like I said, as you progress, the units will tell you sometimes how to get the answer. You think about the units you need, and that tells you what to do with your numbers, all right? All right, let's multiply the top. 1 times 4.5 times 253 equals, divided by parentheses, 0.6 times 293, close parentheses, equals, I think I've got 6.48, which makes sense because it appeared as though we had a greater volume change than we did temperature change. That is liters. I always like to check that. 4.5 times 253 equals, divided by parentheses, 0.6 times 293, close parentheses, 6.56 this time. That's weird. Maybe you got that too. Ooh, I'm hungry. Oh, I got 0.48. All right, I got that one, 5.8. Tell me if you got something different. Okay, and so notice that in all of these, and we're going to end this, we have a set of initial conditions and a set of final conditions. Things are changing because our next step will have to do with when things are not changing. Okay, we'll have one more new gas law. All right, sorry, that was kind of long, but there you go.